All right, let's recap the lecture we watched from another professor on the definition of electric flux, and then use that to do a few examples related to flux, which will ultimately motivate this thing called Gauss's law. Something that is perhaps one of the more fundamental ideas of this course, though admittedly is one of the more abstract ideas in this course. So we want to get the gist of what this law is trying to say. But to do that, we need to understand what electric flux is. So let me recap a couple of the few ideas we need and then give a motivator. Let's start with the idea of the dot product. We're going to need the dot product. That's just math. So recall that we might call it the scalar product, because you can take two vectors and do something with them, and it returns back a number. And so it's thought of, since it involves multiplying components of vectors, it's sometimes called scalar multiplication of vectors. There's lots of different terms, all have pluses and minuses to their definitions. But let's define the dot product of two vectors, a dot b, as either the computational formula, which just means you just add up the components, you multiply the x components together, the y components together, the z components together, then you add all those three terms up. Or we can define it as the magnitude of both vectors multiplied together, all that multiplied by the angle between the two vectors. So this is the geometric definition of the dot product. So vectors b and a, there's some angle between them. If I were to take the two vectors and kind of draw them so that they both start from the same point, that angle is defined based on this dot product and the magnitudes. You did this in intro physics, I'm sure, right? Where given a dot product, I could then solve for, say, the angle between the two vectors. This is a way of defining that angle, for example. The second thing that we'll pull from, we did not really do when we were doing Coulomb's law in E fields, because there's actually a lot of literature that suggests that this actually leads to more confusion. And that's the idea of electric field lines. When we were talking about electric fields, we were always drawing a bunch of little arrows that were, we called it a vector field. Everywhere in space, we drew a little arrow that corresponded to the direction, and the length of that arrow gave you the magnitude of the electric field at that point. We can do the same thing with electric field lines. So if we take, for example, just a single point charge, rather than drawing a bunch of arrows, I could draw a bunch of lines that go out from this charge. And they point away from the positive charge, like we know that it should. In contrast to the negative, all the arrows point towards. And if I were to just zoom in at any particular point, like this point right here, I would see that the electric field points in the right direction. So the electric field lines, we say, are tangent to the electric field vectors. At every one of these little points, if I were to pick a random point, the direction of the electric field, or the arrow that is drawn there, is tangent to the actual electric field vector. And then the other thing that it adds in is that when you draw lots of these field lines, you draw them such that the density of the field lines corresponds to how strong the electric field is at that point. So in these two examples below, we've seen and done for two plates that the electric field is uniform in between the two plates. So notice at any point, if I were just to randomly pick a little point here or there or there, the density of the field lines, how crammed the lines are together, how spread apart they are, is the same everywhere. What that tells you then is that the electric field is uniform. As opposed to the dipole, where if I were to pick a random point, say here, notice that the electric field lines are kind of getting farther and farther apart from one another. There's fewer electric field lines kind of in a box here as compared to a box here. Where here, since they're all kind of crammed together, that is suggesting that the electric field is strong at that point, relative to, say, out here, where they're more spread apart. So how the density of the field lines then is supposed to say something about the magnitude of the electric field. So there are kind of two rules, I just kind of stated those two rules, that when you're drawing electric field lines, they must be tangent to the electric field vector. And the density of the number of lines relates to the electric field. This new feature where it spell checks me, it's unfortunate because I don't think it can read my handwriting very well. Whatever. One thing we can also say about electric field lines is, I could ask on a quiz or something. Let's just do a small, quick example off to the side. Where I could say, here's a positive charge, here's a negative charge, and then maybe I give two examples of the same thing, and I could ask which one of these is the correct drawing of electric field lines. And suppose the top one kind of goes like this. There's arrows that do this, and arrow that does that, and arrow that does that. As opposed to if I were to draw one down here, which maybe does this, and does this, and then does this, and does this, and has something that goes out like that, and maybe this goes like this goes like this goes like this. And I could ask which one of these is possibly correct. One of these is clearly impossible. One of these could possibly be correct, if I then go back and I'm very careful about what the electric field actually is doing. Now, the top one you'll notice is I just drew the dipole again, but the bottom one I drew something different. Particularly, there are these cases where the electric field is crossing each other. And that is impossible. Back to rule 1. If the electric lines are supposed to be tangent to the electric field vector, then electric field lines cannot cross. So I might say here, E lines cannot cross. And why is that? Because again, if they do cross, right, you cannot uniquely determine the direction of the electric field. You cannot uniquely determine the direction of the electric field if they cross. For example, if I have an electric field line that's doing something like this, then at this point here, since it's supposed to be tangent to the electric field, I know this is the direction of the E field. And then here, this should be the direction of the E field. As opposed to, if I have two electric field lines that are crossing, then at this point, I know the electric field is going there. I know here, looks like the electric field is going there, tangent to those lines. But then here, right, is the electric field going this way, or is it going this way? It's not uniquely determined. That doesn't make sense. To have points in nature where it's ambiguous what the electric field is doing. So electric field lines cannot cross. And that's a result of rule 1. I'm going to actually move this. We can use this fact, the idea of electric field lines. Oh, I guess I should say one more thing. That I think this is the reason why sometimes these add more confusion. We cannot, I'm going to write it down even, we cannot think of these electric field lines as trajectories or paths. These E field lines are not paths or trajectories. Of charges. They are simply stating what the electric field is pointing at, is pointing towards, which does then connect to a force. And the electric field line, then if I have a charge somewhere within the electric field, that connects to a force. It's not a force, the electric field is not a force, but if I have a charge in an electric field, that charge feels a force from that electric field. And then that causes that charge to accelerate, which will cause the charge to move, but the path that it ultimately takes is not then immediately equivalent to the electric field. For example, using this image on the right, if I were to place a little point particle here, and say it's a test charge, so it's a tiny little positive charge, the force it initially feels does indeed point this way. Right? The electric field points that way, and then when I multiply it by whatever that charge is, Q times E, that then turns into a force that then points in that up direction. So it initially will start to feel an acceleration towards that, in that path. It might start to speed up and speed up and speed up. And then as the electric field changes direction, the force it feels changes, but the path it might take might end up being something that looks kind of like this. Not necessarily following the field line exactly, though in that case, maybe kind of close. Now here's another example. Suppose I put a charge here, and it's initially moving in this direction. So it initially is just kind of moving to the right, but then this electric field then starts to exert a force on it. It would feel a force that points, again, if it's a positive charge, the force it feels is in that direction. But that doesn't mean it automatically starts moving in that direction. What it would do instead is it would kind of do this, and it would start to kind of veer down because the force is pointing down, and then eventually the force is pointing backwards once it gets over here. So in that case, the trajectory, the path it takes, looks nothing like the electric field. So do not think that these are the paths, that if I were to drop a charge inside this electric field, that's the path the charge is going to take. I think that's kind of one of the big misconceptions that lead to confusion. These are not paths. These are just drawing. Again, that's kind of why I like the vectors better, because the vectors are drawing little arrows at every point. And essentially then if you connect all the arrows, you get these electric field lines, more or less. Then you add in the density. But again, these aren't paths. They're just telling you kind of the direction and overall magnitude of the electric field. So, let's have a motivating example of why we should care about electric field lines and this idea of flux. Let me take, for example, this dipole. You have a charge of 2Q and then a charge of negative Q. I could draw some electric field lines, and they would be drawn kind of like what I've drawn there, or what a computer has drawn there. And notice you can see where the electric field is stronger and where the electric field is not as strong, and there's the path, it is a dipole in that there's a positive and negative charge, but since they're unequal in strength, it's not completely symmetric on the left side versus the right side. What if I just focused on counting field lines, right? If field lines, right, if the number of field lines in a certain region is supposed to relate in some way to the strength of the electric field, what does counting field lines tell me? Well, if the number of field lines are supposed to relate to how much, to the strength of the electric field, I know that a way to get a strong electric field, electric field lines bunched together, would be to have a lot of charge nearby. Lots of charge, strong electric field. Versus where there's no electric field, right? An easy way to get no electric field is to have no charge around. So let's try doing something where we're just going to count electric field lines. And I'm going to focus on counting field lines that are going into and out of surfaces. So we're going to count field lines going in and out of boxes that I'm going to draw. So let's take box 1. In box 1 on this drawing, I'm going to draw up here, I'm going to draw just a box that looks like that. I'll put a 1 next to that. That's going to be box 1. And I'm going to count how many field lines go into the box, and then also how many field lines come out of the box. So if I look at how many field lines are going into the box, that are piercing the surface, right? It looks like this field line here pierces the surface. So there's one field line there that enters the box. There's another field line here that enters the box. And then there's another field line here that enters the box. So it looks like 1, 2, 3. 3 field lines enter that box. So if I have kind of I might say that kind of 3 field lines go into the box. And then if I look at how many field lines go out of the box, it looks like this field line goes out of the box there and leaves. This field line goes out of the box there, and this field line goes out of the box there. So all 3 of those field lines that go in also come out. So it looks like 3 go out of the box. And so then out minus in, looks like then it's 0. And just to help us see what we're aiming towards, if I also ask how much charge is inside the box, or I'll call Q enclosed. In this case, there's no charge inside the box. There's no positives or negatives inside that box. There's a charge here and a charge here, but inside this box there's no charge. If I just focus on just inside the box and nothing else. Okay, that's fun. Now we can try something else. Let's try box 2, which I'm going to draw as a box that is only around that positive charge plus 2Q. Now then, if I start counting field lines, it looks like in this case, maybe I'll zoom in. It looks like, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. 26 field lines that are going out of the box. Right? All those field lines started from this charge, right? And they all started and then eventually left the box. So it looks like all 26 of those, pierced out of the box. Again, following the arrows of the field lines. But then no field lines go into the box. There are no field lines that have an arrow pointing inside into the box in this case. So it looks like here I can say that 0, oops, be consistent with our colors, right? That 0 go into the box, but then it looks like we had 26 go out of the box. So out minus in looks like it's plus 26. More field lines go out of the box than go into the box. And it so happens that there's a charge of plus 2Q inside the box. If I just look at what's going on inside the box, there's this big old 2Q charge. All right. What about box 3? Which you might be able to guess, we're going to have that one hug the negative Q charge. So again, if I zoom in, it looks like there are some field lines, but notice now there are only field lines going in. all these arrows point into the box. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 field lines go into the box, but no field lines go out. None of those arrows leave the box. They all go in and then end their journey on this charge. So in this case, box 3 looks like, said 14 go in, 0 go out. So then the out minus in looks like it's negative 14. And that also happens to be where there's negative Q charge inside the box. So notice, perhaps, you might start to notice that there's a trend happening. When there are more field lines exiting, it seems like we were able to say Q in charge was a positive Q. In this case, 2Q. And then when there were more field lines entering, the total charge inside was negative. And it seemed, roughly, based on these field line numbers, that 26 is not quite 2 times 14, but it's pretty close. So maybe something's going on here. Let's try another one. Try box 4, which I'm going to draw as a box around both charges. Now what might we expect? Now we have to be a little bit more careful. I've kind of done this already in advance. But just to point out things of what you have to think about, there's a bunch of field lines that seem to be leaving the box. Right here's a case where it leaves the box. So those would be cases where it goes out. But then there's also a case where it kind of goes out here, loops around, and then comes back in here. So we have one out, and then also one in. And then notice this one goes out, this one also goes in. So out, in. But then this one seems to only go in, and this one only seems to go in. So when I do the counting here, I get something like that. For this box, it looks like I have about 8 going in when I count. But then I have 20 going out. So 20 minus 8 is positive 12. That there's more arrows pointing out of that green box compared to going into the green box. And then also notice, what is the net charge enclosed? Well, there's a plus 2Q and then there's a minus Q. So overall the net looks like it's plus Q. And notice that 12 is kind of close. 12 plus 12 related to Q, negative 14 related to negative Q, and 14 and 12 are kind of the same thing, and they're about half of 26, which relate to 2Q. Final example. What if I had some sort of crazy box? So box 5, and maybe box 5 is going to be also around this 2Q, but that's also going to do kind of this weird thing here where it's going to kind of go over here, and that's going to be my box. And it doesn't even have to be a box. Like maybe this corner, right, kind of does that, right? But it's some closed surface. It's kind of a weird looking box, but I can still ask the question, how many field lines pierce into that thing versus how many field lines pierce out of the thing? And here's what's interesting. When I do this calculation based on the drawing, I get only one field line pierces in. Let's see, probably might as well be able to find it. I guess it's right here. Oops. This thing here. It's the only place where I see it kind of piercing in. Missing any? No? I think that's it. But then there's lots of them piercing out. I get 27. And again, there's kind of the obvious ones, like these are piercing out, But then also you have to be careful because this one is also piercing out, right? Because it's leaving the edge of the box. It's leaving, going from inside the blue box to outside the blue box. Here it's entering the blue box, but then it leaves the blue box again. So it pierces in and out. This one in particular goes out of the box, then it goes into the box, then it goes out of the box again. So that'd be 2 outs and 1 in for that particular line. So then out minus in, plus 26. And then what is the total amount of charge inside the blue box? Well, again, remember that was just 2q. And look at that. Right, this case where box 5 seems to really match box 2. They both had the same amount of charge inside of it. There's 2q inside both of those boxes. And it did seem then, as a result, when I counted field lines going in and out of the box, there seemed to be some sort of relationship. It seems like there is a connection. There's a connection between the number of field lines I guess kind of, the number of field lines kind of piercing a surface. And I'll be explicit, piercing a closed surface. Notice for all these we drew a closed box. I didn't just draw a line. They all were, closed surfaces. Right, the number of field lines piercing a closed surface and the net amount of charge. Inside that surface. There is a connection, and it's called Gauss's law. But we have to be a little bit more quantitative here, right? Even just going back to my example, right? The connection doesn't seem to just simply be counting field lines, because we didn't get, for box 2 and 5, we did kind of get consistent answers of plus 26 related to Q. But then box 4, right, I might have expected we would have gotten 13 lines. Of course, if 26 corresponds to 2Q, then maybe 13 was supposed to correspond to Q. And then maybe for box 3, I should have gotten negative 13 corresponds to negative Q. So, and that's a result of the fact that it's not exactly counting field lines. I also have to take into account how much the field line is passing through the surface kind of perpendicular versus parallel. If I want to talk about piercing through, this is an example of piercing through a surface where something that's kind of just skidding the surface, tangent to the surface, that's not piercing through. And then something that's kind of at an angle, right? There's a component that's kind of going through the surface, and then there's a component that's going tangent to the surface. That, plus if the number of field lines is supposed to correspond to the magnitude of the electric field, maybe we can be a little bit more quantitative with some physical numbers like the magnitude of the electric field, as opposed to counting field lines, which is a little bit more arbitrary in how you draw it. So this is how the previous lecture, I think, defined, right? They might have defined electric flux this way. Let me define it in the way I think makes sense to me. So consider a small area. It doesn't really have to even be small. Maybe I'll take away small to not confuse it. But so consider an area and I'm going to write delta A. Why delta will become clear, because this is going to ultimately become calculus. And some rectangular slab. It is some plane, a sheet or something. I'll use my calculator. It's some rectangular slab that is oriented in some way in 3D space. And the question is, how can I describe how this slab is oriented? Is it oriented like this, or like this, or like this, or like this, or like this? Now, how is it oriented in 3D space? We can do that by defining a single vector called the normal vector. Let me get a different color. And this is a vector, which I'll call it delta A with a vector sign. And this normal vector points perpendicular away from the surface. That defines the orientation, and we call it a normal vector. Normal is a mathematical fancy word for perpendicular. You know, in physics math context, normal, I'm not making a subjective comment about the slab. I'm just saying that the normal vector is perpendicular to the surface. And we've seen this kind of thing before when you did rotation in Intro Physics 1. If I have a spinning disk and I want to describe how the geometry of how it's spinning, then you probably argued that a position vector that points to a location on the disk doesn't make sense, because the position of every point on that disk is constantly changing. Okay, here's a book. It's easier for me to spin. Right? If I have a position vector that points to the barcode, right? That barcode is the position is changing constantly as it spins around. Similar for velocities and accelerations. But then we defined, when you're talking about rotation, we had a vector that pointed perpendicular to the surface. And then by the right, so I can imagine my thumb kind of being this vector that points perpendicular to the surface. And if I use my right hand and use that thumb, then my fingers kind of curled in the direction of rotation. So I could define a vector that if it pointed up by the right hand rule, that signified that it was rotating this way. And if I had a vector that points down by the right hand rule, then that defined that it actually was rotating in the opposite direction. So you've seen this before with this idea of a vector that's not in the surface, but it's pointing perpendicular to it, but it defines something about that surface. So this normal vector it will point perpendicular to the surface, and the magnitude of the vector will then just equal the area of the surface. Now again, in analogy, we define an angular velocity vector in Physics 1, where the magnitude corresponded to how many radians per second the thing was spinning, and then the direction by the right-hand rule gave you an orientation. Here we don't even necessarily need the right-hand rule at all, right? It's just an arrow that defines the plane perpendicular to it where this slab resides. So now if we want to talk about ultimately this definition which we call flux, which we want to talk about how much of the electric field is piercing the surface. So let me redraw. So we have a normal vector, which I'll try to be consistent, stick with blue. Here's my normal vector, delta A. And suppose I have an electric field that's kind of uniform and it's kind of going in this direction through the slab. And it's the same everywhere. So it's a uniform electric field. It's kind of going in that direction. So in this case, right, again, get back to my book. Right, if this is the slab, right, and there might be an electric field that's kind of going straight through like this, in which case then the normal vector, for the book would kind of point this way, and then also the electric field would point exactly the same way. But it could be that the electric field is kind of going horizontal, but then the slab is oriented like this. So the electric field vector points this way, but then the normal vector points this way. So there's two vectors, and they're at an angle with one another. In this case, if I want to talk about how much of the electric field is going through that slab, and motivating this idea of flux. If I want to ask myself how much of the electric field pierces through that slab, well, this electric field, and let's focus particularly on the vector that I drew going through, the electric field has a component that goes through. So we have this part right here, which that part is the component that does pierce the slab. But then there's this component here. I'm going to get rid of this one. Too busy. Then there's this component here that doesn't go through the slab. That's the part of the E field that is, so that component kind of grazes. Is that the right word? It's not graces. Yeah. Well, that's the component that doesn't go through, but it kind of goes alongside, right, the slab. If I were to break the electric field of vector into two components, right, this component and this component, then there might then, think of horizontal, which is the easy case, right? If the electric field is going in this direction, there's a horizontal component that's the part that goes through, and then there's the vertical component that's not going through. But I could, there's no reason why the slab has to be oriented like this, right? The slab is oriented like this, and this for the electric field, right? There is a component of this electric field that goes through, and then there's a component of this electric field that is going kind of tangent, or just, is right alongside. So, it seems like really, if I were to go look at this drawing, we had the slab itself, which now I'm not really caring too much about. I had a normal vector which pointed this way. Then I had an electric field that pointed this way. And I only cared about the component of the electric field that was parallel to that delta A. I only really cared about only the E part parallel to A goes through. But geometrically, or if you look at this, there's some angle between those two vectors that it seems like the part that's parallel to E, right, that is just simply the magnitude of E multiplied by the cosine of the angle between the two vectors. This is the part of E that is parallel, I'll draw as two lines parallel to delta A. That's the part that matters. This smells like a dot product. So then we can define, then we can also ask, if I'm asking about how much electric field pierces through the surface, it matters whether or not the surface has this much area or say this much area, right? More electric field can go through this big surface compared to something like this, right? As opposed to something like this, which has a very small area. Not as much electric field could go through this smaller area. So it seems like we only want to care about the electric field component that's parallel to A, and it seems like we need also how big A is, right? Is it a big book? Is it a small book? Is it a small slab? Which also is involved in the dot product. So let us define electric flux. We'll use capital Greek letter phi. Electric flux as the following. and actually I'm going to define it as delta electric flux. For a uniform field, a uniform electric field, passing through some area, some slab, with area delta A, which is oriented by some vector, right? Delta A as a vector, right? Such that the area or the magnitude of that vector is delta A. Let's define this flux as. So delta phi equals simply the dot product of the electric field with that vector delta A, which we know is the same thing as the magnitude of the electric field times the magnitude of that vector delta A multiplied by the cosine of the angle between them. That's just the definition of the dot product. Let me rearrange it a little bit, as I'm going to write this as E, the magnitude of E times the cosine of the angle between them, all multiplied by the magnitude delta A. Because then this electric flux definition really is telling us the exact same thing. This magnitude of E is related to, say, the number of field lines. The fact it's multiplied by a cosine, it's the number of field lines parallel to the delta A vector. Which, just so there's no confusion, I guess, right? It's parallel to the vector that defines this area, but then really it's the electric field itself, right? It's the part that's perpendicular to the actual slab, right? To go through it, right? We're talking about the electric field that is perpendicular to the slab, which then is parallel to the vector that defines the orientation of the slab, right? So parallel to the vector A. Or we might say kind of perpendicular to the slab itself. And then that then includes how much area, multiplied by the area of the slab, delta A. So it takes into account the number of field lines that are piercing a surface, and also therefore takes into account how big that surface is. Notice this is a scalar. It is not a vector at the end of the day, that we call electric flux, that goes through some sort of patch. And the idea of flux, I think the other video kind of used as a motivator, or let me just give another example. Right, you could take the flux of, if I have a bucket and it's raining, straight down, and I want to ask myself, how quickly could I fill up this cup? In order for rain to fill up this cup, it has to enter the surface, which is the top of the cup. Right, so you can think of this kind of circle at the top as the surface. And so the flux through that surface then means that the water ends up in the cup. So in that case, you might talk about flux as when I just hold it kind of perpendicular, so the rain is coming straight down, but then the surface is kind of perpendicular, is perpendicular to that direction. Then, the dot, the vector for the rain would be pointing kind of down, and then the vector that defines the surface, right? Remember, that's a vector that points perpendicular to the surface, so it might be a vector that points up or down. And so then the dot product, right, the cosine would be either a cosine of 0 or 180, which is either 1 or -1. And we won't worry so much about the what negative and positive means at this point. But I think we agree that that would fill up the cup the fastest. As opposed to if I take the cup and I kind of rotate it a little bit, then rain is still coming down, but then not as much rain is going to enter the cup when it's off to the side like this. So it's only kind of this region here where rain will kind of fill in the cup, as opposed to here. Then obviously the extreme is if it's perpendicular, rain is coming straight down, but then this surface is defined by a vector that goes to the left or to the right, and the dot product of this vector with this vector is going to be 0, because it seems like their a cosine of 90 degrees is 0. Flux and fluid dynamics and whatnot also takes into account kind of how fast the rain is falling and stuff like that, which thankfully we don't have to worry about. We're essentially just asking about for a field, how many field lines are piercing the surface. So, and that's worth a highlight, I think. This definition is for a single patch, where I said the electric field is kind of uniform over that particular patch. Let's build up in sophistication to a more general definition. So if your surface has multiple patches, then you can define the total flux as you just sum over the patches. So I might define the total flux as the sum, terrible sigma, as the sum of over the individual patches. Right, so I just, for each patch. And then that defines kind of the total flux through a particular surface, which itself might be comprised of a bunch of different patches. Right, so the idea might be, suppose I have not a full box, but maybe I have just 3 sides of a box. Right, so I kind of have the back, the 2 back sides, and then the base. And then I might have an electric field that might be kind of going, something like this, and kind of goes through, that side, and then maybe this one kind of goes through and out this way, and looks like that, and but then maybe this one kind of goes through and just kind of keeps going. I don't want to make it look like I just made field lines cross, so I'll redraw that one that kind of goes out the back. And maybe it looks more like that or something. So in that case, right, there's some field lines that are piercing each of the surfaces. I can even highlight them specifically. Right, there's kind of this surface, which you might talk about the flux through that surface, then the flux through that surface, and the flux through that surface. And then I could add them all up and then define that as my total flux. Now in this case, notice that the 3 surfaces might have different, they will have different vectors that define their orientation. Kind of one is oriented like this, so the vector might point this way. One is oriented like this, so the vector might be pointing that way. Then one is pointing like this, so maybe the vector is pointing down or something. So you get very busy. So in this case, you might have, for the bottom surface, might have a vector here that's that delta A. For the red surface, there might be a vector that kind of points out from the center. That's that delta A. And then for the green surface, there might be a vector that points that way. That's delta A. The convention is that for a closed surface, the delta A's kind of always point away from kind of the inside, points from the inside out. In this case, it's not really closed, right, because it's only 3 sides. It's not a closed surface, but I'll follow that convention anyway. as long as you're consistent, you just have to be consistent. And usually we'll be thinking about closed surfaces moving forward anyway, so it'll be kind of obvious how to define delta A. Always do it from the inside out. Maybe I'll write that down, so in case I forget to say that later. For closed surfaces, the convention is that delta A points from the inside out. So let's do a simple example. Suppose I tell you that there's an electric field that is completely uniform and has a magnitude of 3 newtons per coulomb, and it points to the right on the page. And then it hits a cube with area kind of 1/4 meters squared on each side. Which just means that every side of the cube has a length of 1/2 meter. So just to draw it, it's kind of like the drawing I had before, but I have the remaining sides included. So in this case, then I have an electric field that is going in this direction to the right, and it hits a cube where each side has a length of 1/2 meters. And I want to ask myself, what is the kind of flux through the entire cube, and maybe I might want to consider some individual sides of the cube in this case. So, how about let's start with, let's just follow the electric field. Let's start with kind of this side here. So first we're going to do what is the flux through the left side of the cube. So I have an electric field. I also need to define the area vector. So maybe I'll just redraw it down here, right? I have an electric field that's going to the right, and then it's going to go through this particular slab, the left side of the cube. So, and then I'm going to stick with my convention above, where I'm going to define the area vector as pointing from the inside of the cube out. So the vector for the area, let's use a different color, might be something like that. So delta A in this case points left, and then the area, or the magnitude of that vector, is just the area, which is then 1/4 meters squared. Now, do I have everything? It seems that in this case now I have everything to determine the net flux. That's where I made the font blue. So the flux through that patch then is the electric field dotted with the area vector delta A. That is the same thing as the magnitude of the electric field times the magnitude of the vector A times the cosine of the angle between them. The electric field we said had magnitude of 3 newtons per coulomb. The area of that slab is 1/4 meters squared. The angle between them looks like it's 180 degrees. So cosine of pi radians, which is just then -1. So then it looks like this is negative 3/4 Newton meter squared per Coulomb. And that is the flux through that surface. And again, with the fact that this is a closed surface, remember our example before where we saw that we associated flux lines going out or field lines going out as positive and in as negative in our kind of motivating example. And that convention is kind of being maintained here. As I'm going into the box, right, that's kind of a negative flux. Then what about then the other side? And this side here of the cube. Well, in that case then, if I were to redraw it again here, then it looks like the area vector is pointing, again, if I use the convention of it points out of the box, it also points to the right. And then the electric field is uniform, so it's still, electric field is still pointing to the right. So then it looks like there delta phi is equal to, again, by definition, the electric field times this new area vector, which is 3 newtons per coulomb. The area of the slab is still 1/4 meter squared. And then it looks like it's cosine of 0 degrees, or 0 radians, because E and delta A are in the same direction. So then that looks like it's plus 3/4 newtons per coulomb. Newton meter squared per coulomb. Now, what about maybe, not red, what about maybe the top slab? There. Well, in this case, the electric field is still going to the right, but then the area vector perpendicular to the surface looks like it's then pointing straight up. To me, those look like those two are going to be perpendicular to one another. There is no part of the electric field that's going through that surface. It's always kind of grazing the surface. So then the flux in this case is going to be, again, E dot delta A, but then it's E delta, keep wanting to write it in the calculus notation, delta A times cosine of 90 degrees, or pi over 2 radians, but cosine pi over 2 is 0. So then there is no flux through that surface. And then similarly, convince yourself that the remaining surfaces of that cube also have no flux going through it, because the surfaces are all perpendicular, the electric field is not piercing any of those surfaces, whether it's this surface or this surface, this surface or this surface. So then the total flux if I just add up all those patches, looks like it was really only the blue and the red that mattered. So there's a negative 3/4 and a positive 3/4, all adding up to 0 Newton meter squared per coulomb. And that kind of makes sense, right? You have a uniform field, right? As much that comes in there's just the same amount going out in that case. There's no net flux. There was some flux going through particular surfaces, but then when I considered the total flux through the entire thing, what came in also went out. No net flux. All right, let's see, where are we on time? Okay, I'll wrap this up in 10 minutes or so. Just going through, actually maybe I'll do another example of the math stuff. Now suppose I have an electric field that is given by 3 in the x direction minus 2 in the y direction newtons per coulomb. So that's some vector. It's uniform. But then I want to ask, what is the flux through a slab defined by, well, let's just stick simple. Maybe this slab is defined as kind of just 2 in the y direction meters squared. So if I were to plot this, x, y, z, the electric field looks like it kind of points 3 in the x direction and 2 in the y direction. So 1, 2, 3, within negative 2 in the y direction. So it kind of looks like the electric field points kind of in kind of that direction everywhere. It's kind of hard to draw this in 3D. So what's the easiest way to do this? Yeah, I guess I can't really draw in 3D, so 3 in the x and then 2 in the negative y, so it kind of looks like arrows that might look kind of like that, but they're all in the plane. There's no kind of height to them. And then there's the slab, which is defined by 2y, so there could be kind of a slab that's out here, and 2y, so it's kind of pointing in the positive y direction. And the area, this area here, if I were to calculate the area, is equal to 2 meters squared. So this is kind of the setup. A little hard to draw by hand. Though in this case, then you have some area that's in the y direction, and then you have some electric field that has a component in the y direction and then a component in the x direction. That then is going through that surface. So in this case, then the flux through that slab is the electric field dotted with the slab. But in this case, since we have the components, let's just do the computational version of the dot product. So then it looks like it's 3 newtons per coulomb, the x component of the electric field times the x component of the area, which is 0, plus the y component of the electric field times the y component of the area, plus the z component of the electric field times the z component of the area. And it looks like that adds up to negative 4 Newton meters squared per coulomb in that case. So there is a flux. Right, notice the electric field is kind of pointing in the negative y direction, where the area is pointing in the positive y direction. So, if this book is kind of oriented this way, the flux it's more pointing something like this. So if you imagine that if we're part of some invisible box, if there was actually a box here, it kind of seems like the electric field is more going into the box at that surface compared to going out of the box at that surface. Okay. So then that's just computational dot product. So then what if I've kind of defined this as saying that the electric field has to be uniform over this rectangular slab. But of course I can think of surfaces that are not boxes or not slabs. What if I go back into this? What if I wanted to talk about the flux going through this surface? If I have an electric field going in this direction. The electric field has to pierce this kind of rounded surface in that case. Or if I had like a hoop or a ring, I'll take these scissors for example, what if I want to then think about the electric field that's going through, not a circle, but kind of this kind of weird shape here. So the electric field might be going through kind of, how much of it is going through this particular surface, which might be some irregular shape compared to, say, a circle. So what happens if you have some irregular surface? So I could say, what if not a rectangular slab? For example, suppose I have a slab that is some sort of oval shape in that case. Or I could still define a delta A vector, right? Some sort of vector here that's perpendicular, where the magnitude of that vector is the area. And it kind of tells me how the thing is oriented in space. But in this case, it's not a rectangular slab. And then I might be asking kind of how much of the electric field is piercing this surface. Right? Or it could be kind of a three-dimensional, right? So it could be, right, we could just stick with our kind of oval, right? What if it's an oval? What if, right? Not thinking of it oval, but what if it's a bowl? I'll make that. And I'm thinking about the electric field that is going through this kind of bowl surface, which has kind of this component here, which might be flat, but not a rectangle. And then there's kind of this surface, which is not flat and not a rectangle. So then what goes on there? For the flat part, I could still define a vector that kind of orients it. And then what do I do for that kind of the bottom of the bowl, where the kind of orientation changes no matter, when you're looking at different spots of the bowl? Well, I kind of just gave the answer away. When I say it changes for different spots on the bowl, essentially what you do, that we're getting towards calculus. We're going to zoom in. For this bowl, I could define for the top part some sort of delta A vector that's perpendicular. I'll stick with using delta A, even though it's not a rectangle. But then for the bottom of the bowl, you can imagine zooming in to see a part of the bowl, in that case, where the area vector might be pointing kind of in that direction, where then here, if I were to zoom in, the kind of slab there looks like it's more pointing kind of in that direction, where then a slab here that's maybe on the back side of the bowl has a slab that is kind of pointing kind of in that direction. So you can imagine taking some arbitrary surface and just zooming in and considering every tiny little piece of area that then makes up that kind of curved surface. So the idea, of course, that calculus is built to do, that we can take something of arbitrary shape, in this case an arbitrary area of this coffee mug, and if I zoom in really close, right, at this little spot right here, it essentially becomes a little rectangle. If I zoom in enough, it becomes flat enough that I can essentially see it as a tiny little rectangle. Then I will calculate the flux through that little rectangle. Then I'll calculate the flux through the tiny, tiny rectangle right above it and below it and to the left. And then you can imagine adding up all of those tiny fluxes through those tiny, tiny little pieces. And then that becomes your net flux. So break surfaces into a bunch of tiny rectangular slabs. In this case, we can even relax the fact that the electric field might not be uniform across those slabs. Because if I zoom in far enough, the electric field might be changing overall. But if I zoom in enough, the electric field itself is also going to be constant over that tiny little slab. And if it's not, I take that slab and I break it down and make it even smaller and zoom in even more until you get to a point where each tiny little piece of the area that makes up the surface has a uniform electric field going through it, through a little rectangular slab. So then we can also say that E is uniform across each slab. As well. Even though it might be a different value on different slabs, for each individual slab, it's still a constant. Which then, in that case, the total flux, which we define to be add up the individual fluxes, over a ton of tiny patches. Well, in that case, rather than writing delta A, because each of those patches, there's the direction tells you the direction of the slab, but then the magnitude of that vector tells you the area of that slab. So then this then is the same thing as the electric field dotted, I'm going to write as dA, still a vector, right? And this is just because of the fact that each of those areas are becoming incredibly tiny. But then when we use dA, we don't write a sum, we write it as an integral. So then maybe I'll go down here. So I can write the total flux is equal to then the integral of the electric field dotted with all of those little area vectors. That's worth a highlight for sure. Right, so over an arbitrary area, I just break that area down into a bunch of small little patches, compute the dot product at each of those patches, and add them all up. So this then is the flux over an arbitrary surface with E also is allowed to be arbitrary as well, with E not necessarily a constant either. And again, you can imagine maybe you do have a nice flat surface, but you have an electric field that is changing. So the electric field strength is different at the bottom compared to the top compared to the left. Well, then you can still do the same thing. I can divide this thing into a bunch of small tiny patches until each of those patches has a uniform electric field in it, even though it's a different uniform field at different spots. But then I can just use this formula, add them all up. So this is the general definition of flux, the integral of the electric field over the area. And then for the next lecture, where this will become key, and let me just state it now. When the surface is closed, which means it's not a ring or a slab, it's a box or a cube or a bowl with a lid on it. We're talking about some surface that is closed. The total flux through the surface does indeed connect to how much charge is inside. Realize how much net charge is inside, which is what's called Gauss's law. that the total flux through a closed surface is equal to, turns out, the net charge enclosed divided by this permeability constant. Or if I want to write it as an integral, the integral of E dot dA over a closed surface, and so usually, let me redraw this. What you'll see it as when you do Calc 3 is we'll do the integral sign, but we'll draw a circle around it. And that just means, it's over a closed surface. Right, you are integrating over a bunch of small patches of area, and by being a closed surface, just means that all those patches then form, some sort of, it encloses a volume. It encloses a well-defined volume. That then equals the charge enclosed inside that volume divided by epsilon naught, which, if anything deserves a box, it's that. Or Gauss's law. There is a relationship to electric flux, which, going back to our motivating example, we saw that there was some connection between how much stuff goes in and out of these kind of surfaces, which we drew as kind of boxes of different colors, and some of them were kind of weirdly shaped. There was a relationship between kind of the net flux and the enclosed charge. Now we can make it a little bit more sophisticated in that we have a more quantitative, more physical definition of what I mean by flux, and that indeed relates to this enclosed, the amount of enclosed charge within that surface. Which again, incredibly powerful, but very abstract, because these surfaces don't even have to be real physical surfaces, right? I've been talking about boxes and bowls and spheres, where you can imagine kind of the what the edge looks like. A volume, if I think of this now as a volume, a book, right? There's clear surfaces on each side, right? And then I could ask about the flux that's going through those surfaces. And that might say something about how much charge is inside. But I could just take the book away and just have, and just kind of imagine the faint ghostly outline of that box. And I could still ask, in that volume, kind of outlined by that, the ghost outline of where the book used to be, I can still ask about flux going in and out of that surface. Even though that's not an actual surface, it's kind of a surface that I'm imagining, I'm creating. What's sometimes called a Gaussian surface. I think that your book will refer to it as a Gaussian surface. A surface that you draw, and then you can calculate flux and charge within it. That is what we will do in the next lecture. Here, we're getting our firmly rooted understanding of flux, and how it kind of, what it physically represents, and then how we have motivated that it will connect to charge inside. And that actually will allow us to calculate the electric field for a lot of interesting shapes with much simpler math compared to what we saw in the past. All right, very good.